Reminder about cell phones to mute or cell phone or airline mode. Thanks for coming, everyone, to the USF Analytics Seminar Series. I'm Terrence Parr, a faculty member in analytics. Today, we're lucky to have Mark Zangari from Quantellia, who's the founder and CEO of this company, to speak to us today. And he has degrees in mathematics, computer science, and philosophy, right?
Throw physics in there as well.
That's right, some physics in there. And so he's been working, well, I'll let him go in more about his background and what Quantellia is doing. But if I understand his abstract correctly, he's essentially pointing out that humans are particularly bad at assessing likelihood. And of course, this translates into risk in business and cost-benefit equations and so on. I believe the research has even shown that, something I was reading recently, that humans are easily outperformed by a rat when shown a sequence of red and green chips with known frequencies. A rat simply does a frequency analysis. And humans have this sort of pattern matching fetish where we try to figure out what the pattern is, and so we get outperformed. But anyway, so I will let Mark tell you more about what's going on. Thank you, Mark.
Thank you very much, everyone, and thanks for the opportunity to come and speak to you. I really appreciate that. So yes, as Terrence was saying, I founded a company called Quantellia a few years ago with my co-founder, Lauren Pratt, who's in the audience here as well today. So feel free when we're done talking to come and chat to either of us if you're interested. And I guess our mission is, I hadn't really thought of it this way, but to get humans to think better than rats, I guess. And the one thing that humans have on their side, I think, that rats don't, is we can use computers. And we can build computers and we can write software. And I guess a lot of what I want to talk about today is a view of data, analytics, machine learning, big data, a lot of the paradigms that we're in today, and set them in a context where sort of look at how well we're actually serving the end users and what the sort of problems our end users really have, and is there anything that we can do to sort of bring on possibly what's the next revolution in computer-aided or computer-supported decision support. And I think there is something to do. There's a call to action here I'm eventually going to make, and if you stick with me, you'll see what that is. So I guess, yes, thank you all for coming, and let's all get started. So this guy here, this is Robert McNamara, and some of you obviously know that
You're over 40, probably.
he was Secretary of Defense during the Kennedy and Johnson administrations, and therefore had a lot to do with the Vietnam War. But that's not why he's here. Before he was Secretary of Defense, he worked at the Ford Motor Company. And he did such amazing things at Ford that they eventually made him president. Unfortunately, he got appointed as president of Ford only 2 months before Kennedy won the election, so he didn't really get a chance to be president of Ford for very long. But it's what he did before that I think makes him interesting to us. And before that, he was a member of the US Air Force, working in something that was then called statistical control. And the reason McNamara became president of Ford was he brought those ideas into Ford after the war. Ford was in serious trouble changing its production from military back to civilian, nearly killed the company. And this guy and a few of his colleagues, that they called the whiz kids, completely turned the company around. They turned Ford from an ailing disaster to one of the most successful companies in the world in the space of about 10 years. And they did it using this idea called statistical control. What is statistical control? It's the idea that you use data to support your management decisions. You use data, you then understand the systems that you're trying to manage. You use the data to gain knowledge about the systems, particularly about the present state that they're in. If you know that, you can make much better decisions than any other way. And he put this to test at Ford, and it worked. It worked so well they made him president of the company. Of course, Today, I mean, you'd be thinking, well, what else could you do? I mean, how else would you think about running a major global complex organization like Ford? Of course you would do this. But back in the 50s and 60s, it wasn't entirely obvious that you could. And one of the reasons was this, data. So we're going to go back in time a little bit. Back then, we still had the same issues. Data still required acquisition. You had to gather it from somewhere. You had to store it somehow. You have to be able to get at it once you've stored it in some kind of structured way. And then once you've got it, you needed to analyze it and figure out what it was telling you. I mean, that was the mission. That's how you run companies, right? Well, let's say it's mid-1950s. That's what data acquisition looks like in 1950. It's rooms and rooms full of people filling in books. And that's a database come 1950. There's someone doing some data mining. And of course, here's our friend doing analytics with his slide rule. So if you think about McNamara's worldview, it's 1950, this is what he's got to work with. And he's saying, I think we can use this to run the company. People are going, oh my God. The logistics effort and the human resources and just the sheer organizational complexity of running data flows with this kind of technology is probably as big or bigger than the primary business activity of the company. So Ford in particular, to actually be able to use this statistical control idea, this idea that you use data to run an organization, had to overcome this, and that was huge. Don't underestimate what a big deal that was in the 50s, 60s, even into the 70s. But of course, computers came along, IT came along, and all of this changed in a matter of 3 or 4 decades. I'll let you take a picture before I change the slide. Data acquisition. Today, we use electronic sensors, we've got self-instrumenting code, we've got data being acquired at rates that, were just unimaginable prior to the sorts of technology we have today. Data storage now looks more like that. Server farms, sand farms, storage farms with, disk space with, more zeros of capacity than, you could even write down. Data mining, we've got complex, powerful tools. We can do all sorts of data retrieval, data analysis on the desktop that, again, unimaginable in McNamara's time. And analytics, of course, makes use of all of that technology as well. So, as you all know, we've lived through, some of us, a revolution that has completely transformed the accessibility of data. And the reason for that was, from McNamara's perspective, that was the first hurdle we had to cross in the 60s, 70s, even 80s, that sort of time frame, before we could start using data as a management tool. We had to get it under control. We had to tame it. We had to manage it. We had to be able to use these kinds of technologies so that we didn't have 10,000 people in a 20,000 person organization whose job it was just to track the data. That just made it unfeasible. Now it's more than feasible. Data is done. We've got it, we've figured it out. We know how to do it, and we're very, very good at it, and we're getting better. And places like the university here make it even better. So, we're on track here, but really we've solved the backbone of this problem. It's no longer the big bottleneck. So if we go back to that original diagram, we've got data pretty much solved. We've got instrumented code, sensors, all sorts of other things. We've got incredibly powerful data management systems, analytics, presentation techniques that are also very powerful and getting more so. So as a result of that, and also of course we've got marketing terms. So we have big data for the data management side of this, and we have business intelligence for analytics and presentation. And this has become a very mature kind of aspect of our business. And because of that, I'm going to change it blue. We've automated it, and all of that's great, but we've hit a break here. Automation did take care of all that. Computer technology did take care of our data issues from from the perspective of Robert McNamara's people. But what about system analysis? What about the next step? I've got all this data, I've got a room full of charts, and I've got the best analytics money and technology can buy. Now what do I do? Now what do I do? Well, you're going to get a chance to answer that in just a minute, so I'm not going to go over too much. But it really sets the basis for what I want to talk about, is lots of people probably talk in the data space to you guys, you're learning a lot about it. It's an established, mature industry. I want to look to the next challenge that we haven't really solved yet, which is once we've got all that data, how do we actually use computers, IT resources, all of that hardware power? How do we actually start thinking about software that can actually take what comes out of the data part of this cycle and use it to understand systems better and make better decisions? And we're all going to do a little example together here to try and kind of highlight what the issue is and then how we might solve it. So just to summarize, we've got a demarcation really between automated decision support, which is in the data analysis presentation phase, and really human-centric decision support, which is more in understanding how the data that's coming to us might affect the systems that we're trying to manage. And another point I guess I want to make is that the role of visualization, why is visualization so important? It's because we've really put that demarc at that location. And visualization is a particularly powerful technique of transferring the information that computer software extracts out of data into the human brain. Why? Our visual cortex is the most high-performance part of our brain. It's the supercomputer that's embedded in our brain. And consequently, we have a very high level of what we call cognitive efficiency when we use visual representations to get ideas into our heads. Consequently, looking at a graph tells us much more at a cognitive level than reading exactly the same information off a table. Those two are informationally equivalent, but we understand a graph much more, or a chart, or something visual, much more than we do text. And as a result of that, we've put a lot of effort to develop software that uses that, and that becomes the preferred way of transferring complex quantitative information into human heads. But there's another activity that our heads have to do that we haven't got software for, and we're about to do it. So, audience participation. Okay, I'm not going to call on anyone, but I want you to sort of sit there and kind of come along with me for this little job exercise we're about to do. So imagine we've all just been appointed as a product manager. Okay, big promotion. Now the last three guys who had this job were all summarily fired because the product that we're now in charge of and that they were in charge of failed so dismally. It lost a ton of money. It cost a certain amount of manufacture, they ordered too much, they didn't market it right, and as a result, the last three guys oversaw a financial disaster. But we're going to do it better, right? We're certainly going to do it better, and we know we're going to do it better because we're numbers people. We understand data, we understand analytics. We're going to put that to use and not make the same mistakes the last guys made. Okay? Everyone up for the challenge? Big pay rise, worth doing. So here's our mission. Our ultimate mission is to make some decisions that will maximize the profit that we return to our organization. And to do that, there's a few things that we can decide about as to how we run our product. The first is, how many units do I order from the manufacturer? So there's a manufacturer that makes the thing, we package it up and sell it. How many units do I order from the manufacturer? What price do I charge the end consumer? And how much of that profit that I make do I reinvest back into marketing my product so my sales go even higher? Now these are the same decisions that the last three guys had to make, and they made them badly, so badly they actually got fired. So how are we going to make those decisions? Well, we need some information, and we're not going to, as I said, do it blind. We're going to use data, we're going to use analytics, we're going to do this right. So there's our data. And I absolutely promise you, everything that you need to know to make this decision is in those two charts in that table. Okay? So what's in the table? Well, the manufacturer charges a certain amount of money to make this product for us. And this table is the unit costs that we incur per unit. If we order 100, it's going to cost us $12 per unit. If we order up to 500, it's $10 per unit, and so on. And if we can order more than 10,000, then they're only going to charge us $6. So that's great. The more we buy, the less we pay, the more that goes to our bottom line. That's great. But we need to make sure we can sell them all, because if we buy units that we can't sell, that's money that we're not going to recoup. That's going to eventually open us to risk of some loss. All right, so how many of these things can I get people to buy? Well, that's where the demand curve comes in. And I did a ton of research. You know, I mean, we did some data mining. We have 10 years worth of history in our database of price versus sales volume, and I ran some regressions on that, and I got a curve that looks just like that. So again, being a good analytics person, I know what I'm dealing with here. If we charge almost nothing for it, almost everyone wants to buy it. But I don't make any money, so there's no point giving it away for free, because sure, we'll have lots of units, but we're not making much money. What I want to do is, there's a balance here. There's a balance between how much do I charge. The more I charge, the more I get, obviously, per sale, but the fewer people buy it. So there's a balance here where that kind of, you know, reaches a maximum for me, this maximum between how much I charge versus how many people buy. It's a very, very common issue that we need to do. So that's information that I need. Now I also need to know something about how effective my marketing is. And basically this chart, or this graph here, tells me, for each dollar I spend in marketing, what's the uplift I get in percentage of sales. So if I spend no marketing, basically it's going to follow that curve at the top. That's my base demand. If I market, then I can increase that by the percentages shown here. And those three pieces of information answer those three questions. I want everyone to look at that and answer those three questions with these three pieces of information. Anyone know how many units I should order? Anyone know what I should charge? Anyone know how much of that I should reinvest? I mean, we've done the analytics, we've got the data. We should have the answers.
The problem set is making some wrong assumptions. Sorry.
I'm sorry?
The problem set is making some wrong assumptions.
Oh,
and
okay.
not just yours, but just generally in terms of like consumption models. So most business models assume that we're interested in the 7 Ps, right? Specifically like the product, the people, the price, the place, etc. So whenever we draw like demand supply curves, we try, as much as possible to optimize them based on, classic operational research type techniques. But there are two key pieces of information which are missing from why somebody might decide to buy something. One of which is purpose. So whether or not the marketing affects them is not an exact science, because the purpose is not a data point which has been collected. The other thing which affects, the assumptions are wrong in so much as, instead of thinking about it in terms of like from the perspective of the manufacturer or the product manager, they should be actually thinking about it in terms of from the consumer's perspective. So the purpose with which they're buying something, and also if they already have like a brand affinity or a product affinity, that's not the type of information which is appearing in.
Actually, I'm really glad you raised those points, because if this is 101 of what I'm trying to say, that's kind of 201. And I'll address it very briefly. I think you're absolutely right that this is not the sum total of the solution. You're absolutely right. This is a grossly simplified version of the problem. But I want to make 2 points. The first is there is actually an answer here. It might not be the right answer. You're right. There are other factors too that need to be taken into account. And I raise that as a question. How would you do that? Okay, let's keep going, and perhaps we can have some discussion at the end. But what formal techniques would you use to do that? And oh wow, we're getting a lot of interaction here.
I think you've got the demand curve on the bottom, you've got the supply curve. Where do they intersect? Isn't that what we're driving at here?
Well, that's not supply. That's marketing. That's marketing efficiency.
You would have to do trial and error and try to do it because it's non-linear. It's very hard to do otherwise.
Yeah. You're absolutely right. The point I'm trying to make here is that data by itself, without understanding systems, without understanding things like, you're absolutely right, this is not a trivial thing to solve at all, doesn't give you the answers. You need to know how those systems work. And things like trial and error and things like bringing in other factors, there's not a lot of product support out there. If you wanted to do that and you wanted IT support to do it, you would probably need to commission a project where someone actually built something for you that did this. Now, our view of Quantellia is that there should be off-the-shelf software that you can plug that information into, press a button, and it tells you the answer. And that's kind of what we built. And I want to tell you that I'm about to show you what I did with this. And that took about 15 minutes of work, in all honesty, to get from this, with these as inputs, I could answer those 3 questions in about 15 minutes. And what I'm saying is that as an industry, we spend a lot of effort producing graphs and charts like this from petabytes of data. And that's worth doing, that's very important. But we spend proportionally much less effort in trying to do things like, well, let's take this data and now embed it in the business context and take things into account like, this is a very simplistic model. Let's try actually capturing some of the complexity of the real situation and have IT tools that help us do that. And that is essentially the mission that I'm trying to kind of evangelize today, if you like. The point is, it's not just data. We hear a lot about how important it is to produce good data. It's absolutely important, but it's more than that, and the real answers don't show up until you've done something else. So what is the something else? So even with all the data that you need, just the data, it's still very hard to make the decisions. There's all kinds of other things that come into account. And the reason for that is what we said before. There's a lot of automation that's available in data. There's not a whole lot of automation that's available in systems analysis. It's doable, but it's still a lot of effort and a lot of expensive. And in some ways, in this box, in the systems analysis box, we're still back where we were back in my earlier photos of the Robert McNamara era, where we've got people essentially manually trying to do these things. I think someone in the audience said, really, to solve that issue, it's trial and error. You've got to try things and see what happens. And you can either do that manually, or even if you want to use IT support, someone's going to have to write some code for you to do that. And the point is, I think as an industry, there's a whole class of problems where we could come up with some really cool products that help people essentially at the touch of a button solve these problems, rather than have to kick off projects or do coding to sort of solve them. Why is it so hard? Well, we're very good at recognizing images. We're not very good at running systems models in our heads. And I think the point about the rats kind of spoke to that. If you've got a set of entailments, A implies B, B implies C, C implies D, and you get some information as to what the value of A is, most people can't go more than 1 or 2 rules deep. Our brains are just not built for that sort of processing very, very well. And as I said a number of times, there isn't a lot of IT support in solving this particular problem. But I want to see if we can change that. And one of the challenges here is, as we said, I think as the lady with the red shirt said, there is actually a more complex model here than just what that data was referring to. And I think one of the challenges that we have in using computer resources to run some of these more complex models is someone's got to teach the model to the computer. It's not a one-size-fits-all situation. Every situation perhaps has a common sort of structure, but every situation also has particulars that are unique to that situation. And what we need is a language and an approach that allows us to transfer that knowledge into the computer so that it becomes computable rather than something that has to be done as a sort of specific one-off case every time. Is there a way we can generalize the information capture process and record it so that these system models become computable? And what that picture is one representation of what's actually going on in that sales model. And what I want to do is just kind of go through that and talk about how we came up with this and sort of why it helps us. And so the next part of what I want to talk about is we call these decision models, and they're basically ways of identifying what the relevant factors are in the decision that you're trying to make, identifying how you're going to specify each of those factors, and then providing that in a way that a computer can then essentially do the trial and error analysis and do it very quickly. So this is a snapshot from the tool that we've created. It's called World Modeler. And each of those boxes, essentially just drag them in off a palette. I can show you later on if you like. You build the model that way by just dragging and dropping, attach some data sources to it, and it then essentially figures out the rest. So what are the elements of this type of modeling? Well, there are things that we call attributes. It's probably not the best name, but it's a common name, I guess, in programming and IT. And each of those are the sort of variables, if you like, or the quantities that the model represents. So there's things like profit, production cost, revenue, all of those things. And we'll get to how we actually identify those and how we link them together as we go on. But those sort of just to identify what the players are in this game. The attributes represent the quantities that we're actually modeling. Linking those, we have what we call dependencies, and that's how information propagates through the model. So things are linked together in various ways, and that's how we do that. And the reason, by the way, that when we got those three charts and we couldn't answer those three questions easily was because that's the problem you've got to solve to do it. And that's more complex than most of our brains can handle, just as a simple reason. But it's actually much simpler than a real business problem. And again, as was pointed out, this is sort of a toy problem. Most of the real complexity has been removed. And the good thing about this modeling approach is it scales. It can scale to solve very, very complex situations and, again, allow raw data to be put in a context where it can provide much more insight than it otherwise could just by sort of staring at the charts. And one objection, I might just take a little aside here, one objection that people often raise to that is, well, wait a minute, no model is exact. So even if you build this model, how do you know you're getting the right answer? And it's a very valid objection, but the response to it is to understand how information supports the decision-making process in the first place. And that is, as nice as it would be to have a crystal ball on your desktop that when you kind of rub it, the genie comes out and says, ask me any question and I'll give you the right answer. That's not how it works, and it's not how it works today. The best that you can do is inform yourself as to what the likely outcomes, or what outcomes are more likely or less likely, given what the data is telling you. And what models do is they essentially transform the information from the variables that you've got data about, which we had data about the demand curve and the marketing efficiency curve. They transform that into information about what you care about, which is how much profit do I make if I order a certain number of widgets. And really that's all they do. So there's no additional magic that comes from this. What it does is it transforms the data that you've got into answers of the questions that you care about. And it also allows you to explore that space systematically much more easily than if you don't have tools to do that. We'll see that in a minute. So, yeah, sure.
So part of the problem with your initial example was that the question you asked wasn't known in advance, basically, right? So that wasn't programmed into the answers that the analytics provided.
Right.
Are you gonna run into that same issue here where I can only answer the questions that I know in advance? I wanna answer like questions about profit, revenue, whatever.
Yeah, well, the whole idea, it's a good question. And I'll respond to it this way. The data that we have is not authorable in the sense that I have a database which has information on sales, and I have a database which has information on price. I can't create a database on profit if the data doesn't already exist. I can't, so the only questions I can answer are based on the fields that I already have data about in the data question. I can transform things a little bit, but essentially that's what the constraint is. The point of this environment is that it's authorable, and the fact that profit is on this chart is because that's what we're looking for, so that's what we put into the problem. So this is a much more dynamic environment where I can create questions and answers on the fly. That's really the whole point. It's trying to give you that agility to say, well, if I don't know the answer in advance, but I've got this information, how might I transform this information so that it does give me the answers that I need, assuming that the answers are available by sort of entailments that I can follow from the information that I've got. That's essentially, I hadn't quite expressed it that way before, but it's essentially that's what it is. It's when the answers that you have don't match the questions that you're asking directly, but they are encoded in there somehow. If you can figure out, A affects B, B affects C, and therefore I get D, what this is a way of doing is showing you how I get from what I do have, which is production cost. I've got that. I've got my unit cost, I've got my demand, and I've got the price that I'm charging. I do have those. Those are the inputs into this thing, and what this does, it transforms it into the profit that I've made. So you're absolutely right that one of the traditional issues is, well, what if I don't have data about the questions that I need to answer, but I've got data that informs that? Well, this is one way you can sort of say, well, this is how you transform that data, or transform the form that the data's in into the questions or answers to the questions you're actually asking. If that makes sense, yeah.
Excuse me.
Sure.
When you speak of computable system model, are you speaking of a general dynamics model following Forrester?
Yeah, pretty
more or
close,
less?
yeah.
Please.
Yeah.
Second, how do you define the correct attribute of a system? Is a set of assumption, more or less? Because we are not sure that the attribute and then the dependencies are the correct
Right.
for that specific system. Okay.
Right, so there's two answers to that. The first is, the next few slides will address that a little bit. The second is, yes, you can't guarantee that you get it right. And this is a conversation sort of we find ourselves in often. You can't guarantee you get it right. But the point is, what else are you going to do? It's better than doing nothing. It's better than saying, well, I'll just stare at the charts and hope I get the right answer. So the claim here is not perfection. The claim here is it's a hell of a lot better and a hell of a lot more systematic and a hell of a lot more auditable and traceable and all of those sorts of things than just looking at the charts and coming up with an answer. So no, the model's not perfect. No, it's not correct. But it's a way of making transparent and much more manageable, and oh, by the way, executable by software, tasks that previously are much more opaque, and if you are going to use software, you usually have to build software from scratch. So again, there's a saying, don't let the perfect be the enemy of the good. That's a concept that I think is very important here. Yeah, sure.
Is this static or dynamic? Is it changing?
Yes, it's changed. It's either of them. You can set it up to be static, but there's also learning rules you can put in here. So, for example, the relationships between these things, you can implement them statically, but you can also have it learn from the data. So that relationship, the model evolves and self-adapts as it processes more data and essentially evaluates its own performance against the data. Anyway, so let's look at this in a little more detail. Part of the process here is to, as we said, how do we build these models? How do we start from scratch and get some sort of representation of what the business problem we're trying to solve is in a way that is then computable. And what we do is to identify certain classes of attributes that have certain roles within the model, populate those, and then use that as the process for building the rest of the model out. The first thing that we try to identify are what we call the outcomes, which is essentially what is it that you're trying to achieve in the problem that you're dealing with. So in our case, it's profit. There's many other potential things that you can have: customer satisfaction, return visits, reduced churn, upsell, cross-sell, all of those sorts of things. So what is it that you're ultimately going to measure to determine the relative success of the decisions that you've made? So we know what our mission is. It's to increase profit. So that's what the outcome is. From the point of view of actually executing the model, this tells the model execution environment that this is something I need to maximize, minimize, whatever. The criteria for success, my utility function, if you want to call it that, is going to be based on these attributes. And in this case, it's profit. We also have things called levers. And these are the things that I actually have I have control over. And one of the things that we often find, I might just fast forward to the next category, so it's on the board, which is externals. Both of those are inputs to the model, but a lot of times there's a lot of confusion in what I have control over versus what I don't. It affects both classes of things will affect the model, but I can actually only control some of those things. Some of those other things are external to me. They may be very important to the result that I get, but I don't have control over them, and therefore they're outside my decision-making structure. So I've just flown in from the UK, right? And everyone knows what London weather is like. So one of my results, in that case, if I was building a model, it would be, I would like to get to the office without getting soaking wet, right? And there's two things that affect that. Is it raining or not? And do I remember to bring an umbrella or not? I could decide that it's not going to rain, right? I mean, that's a key part of my result. Is it raining or not? I could decide it's not going to rain, and that's how I'm going to base my, chances of getting to the office. Well, it's not a great decision because I can't actually control whether it rains or not. That's external to my decision-making structure, right? So I need to know what the answer is, but that's not something I can affect. It's going to affect my result, but it's not advice that I can give. I can't tell people, if you want to stay dry, just stop making it rain. What I can do is bring an umbrella. That is something I do have control over, and that is a sensible directive to give. That's a sensible result of the analysis of this problem, is bring an umbrella to work. And that's a really key distinction. Both of those things are inputs to the model. So from the execution environment, they're sort of the same because it's things that you vary to sort of explore the solution space. But from the point of view of actually giving advice back to the business or giving results that the business can actually use, levers are important because those are the ones that they actually can take action on. And that distinction is, again, very important in terms of giving what, you often hear people talk about actionable intelligence. Actionable, one way to translate that, and of course it's not the only way, but one way to translate that is give me the values or give me the behavior of levers that I can actually set, as opposed to information that it's good to know, but I can't do anything about. So in our case here, there's the market size, that's independent of my control. The demand function, I assume, is external as well, the base demand function. And the cost, again, I can't control that. That unit cost table, again, is outside my control. The dependencies are how we link these things together. And that introduces another type of attribute that we call intermediates. And what they are is oftentimes when you've got the inputs to the model, so we've got our three levers there and our three externals, and this is what we're trying to achieve, the profit. I can't get there directly. So the retail price does affect the profit, but not directly, because there's things like cost and how much I spend on marketing and various other things that also affect the profit. So I need to calculate those internal quantities to get to the answers that I want. So we call those intermediates, and they link us up. But of course, there can be more than one layer of those. There can be several of those within the model. And that that defines the basic classes of attributes that we do. So a lot of the work here is understanding the business situation and decomposing it using these categories. The thing that's useful about them is, first of all, most people understand them. So if you're non-technical and you're dealing with subject matter experts within the business, they sort of understand these concepts fairly well. But they also translate to things that are meaningful when you're executing the problem in a computer situation, because there's the inputs to your utility function, those are the independent variables that you vary, and then everything else in the middle is the equations that you use to basically link those up. So we found that it's an effective way to bridge subject matter expertise that's non-quantitative necessarily into being able to build essentially a quantitative model that takes this input data and gives a result that's meaningful to the stakeholders in the business. The dependencies are essentially where, if you like, the math comes in. That's where we actually link things together with equations. So in this model, most of it's pretty simple. For example, how do we get profit? Well, profit is revenue minus the production cost minus the marketing spend in this particular model. And that's borne by that dependency there. Right? We're not showing all of it. It's dependent on the other two attributes as well. But each one of those links you can think of potentially as having one of these expressions on it. And that's how we kind of get from A to B. Another way of doing it is saying that rather than an expression defining that link is defined by essentially a regression equation from a data source, which is what we do to get from price to the number of units. We use the demand function to get us from price to units or units sold. And that's exactly what the demand curve is. So we wouldn't write it, we could write an equation for that, or we could just perform a regression on that curve, or that curve is the regression, that's the regression output of the data that we've got, and then it specifies how those things are related. And looking ahead, when you sort of analyze how is data used actually to solve these sorts of business problems, one of the ways is that it actually specifies these point-to-point relationships between the various building blocks of models like this. That is what data informs us about. And then somehow we have to kind of fill in the rest. And what we're trying to do here is come up with a way where we can use software assistance to try and fill in the rest, rather than trying to do it in an ad hoc way or just in our heads. And I should clarify too, there's really two pieces to that. One of the pieces is the software itself, but the other is a common methodology. One of the things that we've benefited from hugely, I went through software engineering, I began in the 1980s when there wasn't a lot of methodology around, which made it hard for us to communicate with other software engineers. You've read all the reports, probably 80% of major software projects failed, and so on. One of the big revolutions in that is coming up with a common language and a common set of techniques. So everyone knows what Agile is, everybody knows what Waterfall is, everyone knows what a requirements document is, everyone knows what UML is. Sometimes. Lots of people do. The point is, though, that there's an understanding that standards of communication and standards of documentation of these things dramatically improve the efficiency with which teams of people work, and the industry as a whole is able to achieve what it's trying to do. And one of the sort of implied suggestions here is we need the same level of rigor, if you like, or standardization around how we solve these sorts of problems in this domain as well. And if we do that, then we'll be able to, first of all, build software products that can interoperate much better to solve these kinds of problems. And second, teams of people will be able to interoperate much more effectively because everyone's speaking the same language. Anyway, so as we said, data, really part of the purpose is to inform how these various building blocks all stick together to actually get us where we need to get to with these models. And a third option that I won't talk about too much, but sometimes you don't know. Sometimes you just don't have data, and writing down an equation is kind of difficult as well. Sometimes the best you can do is what we call a sketch graph, which is basically you take human expertise and you ask the people who know, listen, how do you think A varies with B? Does it get bigger? Does A get bigger if B gets bigger? Does it get smaller? Is it a sharp increase? Is it a small increase? Is it sort of lumpy? How do you think it works? And sometimes that's the best you can do. And so being able to accommodate the fact that these systems are inherently fuzzy and you need to be able to deal with uncertainty is the key part of this. And there's a whole subsection on uncertainty and risk and those sorts of things that we could talk about. But I don't want to focus on that. But I do want to mention that embedded in this is systematic ways of dealing with uncertainty. And this concept that, again, it's almost a cultural change. The model doesn't tell you the right answer. It informs you about what is more likely or less likely given certain circumstances. And the fact that there's not always data about everything should not stop that benefit from being delivered to the end stakeholders. So, as I said, there is a fairly deep systematic way of dealing with uncertainty, sensitivity, precision, and so on. So just as an aside, some of the work we do is with the intelligence community, and they have a very complex data quality metric structure that we have to propagate through these models. So they'll come up with a conclusion, and there's all sorts of things that have gone into that conclusion. And some information ages. If I saw some bad guy at a shop talking to some other bad guy, that's useful information if it happened yesterday. It may not be useful anymore if it happened 2 years ago. So there's a information sort of currency deflation that goes on with time there. And there's all sorts of complex factors. But again, if you start mapping out models like this, you can propagate that through the entire model. So it also provides you with a way of very systematically dealing with uncertainty and data quality metrics sort of all the way along. Another point too, I just wanted to draw out a distinction. We talked before, and we all experienced to some extent just how bad we are at processing system models in our heads. We're not very good at it. But it turns out we are very good at analysing them. In that I bet there's probably no one sitting in this room that if we sat down with the exercise of saying, take those 3 pieces of data I gave you, how would you actually calculate the likelihood of profit from that? We could all figure it out pretty easily because we're very good at this decomposition process. We're pretty good at saying, just about everybody could figure out the profit. Well, that's going to be revenue minus our costs, right? We know that, so let's write that down. And then what are our costs? Well, there's a production cost, there's a marketing cost, and those are our 2 costs in this particular model. And we're very good at this sort of decomposition. So while running the models is difficult, building them is not. And that makes for a really nice human-computer partnership, right? The computers do exactly what we are bad at, which is executing these models. We do what the computers are bad at, which is figuring out what the model should be in the first place. And there's a very nice partnership there. I sometimes say it's a bit like the poet and the word processor, in that the poet still writes the poetry, but it's nice if he's got a thesaurus online and the ability to delete words and so on. So, as with most human-computer partnerships, we do the creative stuff and the computer does the drudgery. So let's finally get to the answer. We started off with this thing: how many of these things should I order? What price should I charge? And what profit should I invest to maximize the profit? Well, what I'm about to show you is running essentially what I think somebody said is really the only way to solve this problem, which is to just do trial and error. And there's a simulation engine built in that just searches the space of all of the different inputs and maps out the profit for each of those. So let's actually look at the result of that. So there we go. Our profit's going up, and there we go. And that star at the top sort of represents about the biggest profit we're going to get with the parameters that we had for this, and it's something like $140,000, I think, in this particular, for 1.4 million. How many zeros there? And if you look at the parameters that go into that spot, it turns out 38,000 units is about the number that we need. We should charge $15, and we should reinvest 7% of our profit back into marketing. And So, great, those are the answers that we've got. Fantastic. So, would have been hard to get that before. Yeah, go ahead.
Where is the axis? Where's the x-axis?
Oh, sorry, yeah. The way this works is essentially each point on that line is a given set of parameters, and this is just the trial number that it's doing. So it's just doing a whole bunch of trials, and there's a search algorithm which looks for that minimum. This is just the trial number. And there's various ways you can project it out so you can see the individual inputs, but again, I've only got so much time, I didn't want to bore you with that. So, terrific. We've taken those 3 pieces of data and we've extracted the 3 things that we care about. How much do I charge? We charge $15. We charge $15. We order 38,000 and we reinvest 7% in marketing. We're not going to get fired. We're going to get a raise. This is fantastic. Well, wait. There's more to this than just that. Because the shape of this thing tells us a few things. First of all, it tells us why everybody else got fired. You go off the end of that curve and your profits are way down here. You're in the negative territory. You are losing a crap load of money. And in fact, you go into that region there and you're losing a lot of money. And if you don't know the dynamics of this system, if you don't understand that, you could very easily find yourself in a situation where you're in this negative part of the curve. And the issue about, again, going back to simple data presentation, neither of those 2 charts, I think, made that obvious. But you have to do this kind of work to extract that information from those 3 charts, or the table of the 2 charts. That information is encoded in there. I use nothing more than what was in there to come up with this. But this is how this system behaves.
Question.
Yeah, go ahead,
So are
sure.
you using Monte Carlo simulation to create that?
Effectively, we can, yeah. We use Monte Carlo with different shape distributions that we can sample from. And we also have various search techniques that we can use on the parameter space directly, like method of steepest descent or annealing, those kinds of techniques. But back to looking at the shape of this curve here, I want to point out that even though the data that we used to perform the analysis here, those 2 charts plus the table of pricing from the manufacturer, even though there was no explicit uncertainty expressed with any of that, there were no error bars, there were no confidence intervals, it was all just fairly precise data that was presented. Even though that was the case, we are able to, with the aid of the systems model, we are able to generate a fairly good representation of the risks associated with this decision. And the basis for that risk is sensitivity. What we can see here is, as we vary through the various decision points that we might have, the green line at the top represents our potential for profit. And as we can see, that was maximized at a certain point, but there's a range of profits that we might get. The red line is our exposure to the risk of loss. And as we can see there's a region to the left where we're not really exposed to too much loss risk at all, but then it gets pretty serious as we move to the right. And in practice, when people make decisions, there is no quote-unquote right answer. There is an optimal answer notionally, but that is modulated by the risk that they're carrying. Let's go back to this model here. It's quite a simple model, although arguably it's probably a little more complex than we might have expected given the data that we were looking at, but still fairly simple as models go. It does, however, have a very interesting feature. And if we look at this chain of dependencies, they form a closed loop, or what we call a feedback loop. When we make a change that alters something about the system, or something in its environment changes, the system doesn't just snap into its new state. There's a dynamic process by which it reconfigures and re-equilibrates and eventually settles down into what that new state will be. And one thing that decision makers are not really aware of, because the data usually doesn't show them this, and if you listen to the media, you can tear your hair out with this particular confusion, is that real systems have feedback loops and those sorts of complex nonlinear structures in them. And they don't just sort of sit there statically with the unemployment at whatever percentage it is and the profits of the company at whatever percentages that they are. Those are equilibriums which are reached at by the system kind of, negotiating with its entire environment and it reaching a level for a time. And we call that an equilibrium or a steady state of a system. But of course, everything is dynamic, and those input variables that equilibrium depends on are being perturbed all the time. And when that happens, the system doesn't just change. It goes through a cycle, and very often it looks something like this. There's an oscillatory cycle called a transient, as the system is kind of renegotiating its new equilibrium point. And this shows up in data all the time. The problem is that people don't necessarily know how to interpret it. So a lot of times when there's a policy change, let's say in public policy, and that gets implemented, you get this wild fluctuation going on as the system sort of re-equilibrates, and then you get a new equilibrium point. So I don't know, hypothetically, a new healthcare system, for example, just say that happened. You will find that in each of the, many of the variables that you're looking at, since there's a fairly significant perturbation to the system, it takes a while before it re-equilibrates. And you need to manage for both of those because systems can only handle so much shock. I mean, you can break, you can kill your business if this goes below what you can tolerate. You can kill a business or kill an initiative or kill something because the transients are too great. And there are various ways you can dampen transients, and those can be modeled as well. And then, of course, you get into the new equilibrium phase. So we'll just put some labels on there for that. And understanding these sorts of characteristics of the data, when you see them in models, again, using our visual cortex and all that sort of stuff, if you can make that visual, it's incredibly powerful, and people start to understand it in ways that they never would have before. So, just to summarize, we've already automated data, that's great. If we take this approach and consider what that's done now, systems analysis box is blue now as well. It's full, it's got lots of automation support. And it also shows what the role of data is. It's not quite as sequential as it looked like in the previous thing. In fact, if you take this seriously, you really start with modeling the system before you go and get your data. Because if you understand your systems model, it's the dependencies that determine what data that you need, and then that then determines, okay, what data do I need to go and get or buy or whatever. And once I understand the sensitivity, that tells me how good data I need. If I've got some variables and there's not a lot of sensitivity between that variable and my outcome, then I don't need fabulous data for that. I don't need high precision, high accuracy data. I just need to be in the ballpark. But if you've got a variable where the outcomes are highly sensitive to that variable, that's where you invest in some fairly serious data acquisition. And we still have a demarc, but the demarc is now not between the data and the systems analysis. It's between the outputs of what the systems analysis produces and the decision. But that's a much smaller gap to jump because, as we saw before, the output of the system analysis simply answered the questions we were asking. How much do I have to buy from my manufacturer? How much do I charge? And how much do I reinvest in marketing? There are three answers. Okay, there's the computer telling me something, but I don't have to interpret that. I don't have to somehow look at the tea leaves and say, okay, what's this really telling me? It's just answering my questions. Having said that, the graph was very useful. So the same sort of visualization approach that worked when we were looking at the outputs of data, it also works very well for the outputs of systems analysis, because again, what we're actually producing, in fact, is another data set. It's not a data set that's measured from operations or from wherever we're getting our data from. It's a data set that's produced as a result of this process. But still, a graph is more useful than a table, even in that case. So visualization is still really important. What's interesting, though, is that, well, before I go there, there's a new, actually, before I go there, the paradigm, again, if you take it seriously, introduces a second class of visualization that we really haven't thought about too much. We've thought a lot about data visualizations. Right? How do I take these quantitative relationships and make them understandable as quickly and efficiently as possible? That's what we generally spend most of our time thinking about in terms of visualization. But there's another kind, which is systems visualization. I've got all of these all these interacting components. How do I understand how they affect one another? So that if I make a decision, how do I understand how that decision will ripple through the world that I'm responsible for? And that's not charts, that's not, I mean, it can be, but it doesn't strike me as that charts are the way to do that. We've got very powerful graphics capability now. We've got new ways of looking at things, and at the end I'll show you some interesting ways that we might be able to sort of display that. Anyway, so just to sum up, we call this approach decision intelligence. That's our marketing kind of spin on that. But it's basically trying to shift the question from what can I learn from this data to, if I make a certain set of decisions, what are the likely results going to be and what risks am I exposed to? And that's the question that we want to be providing answers to. And that's the question that the software that we build should be trying to answer as quickly and cheaply as possible. As we said, if you think about it, it provides a framework for the most effective use of data and analytics because it gives us that sort of systems model into which the data plugs in. And the other thing that we find is that once you've got these models written down in this form, they provide a kind of institutional memory. People go back to them all the time because now you've got a big chart on the wall that sort of shows you how everything works, that everybody can use and everyone can understand. And that becomes a really valuable information resource, it turns out, that lots of organisations, at least the ones that we've dealt with, have got almost as much value just from that in their internal kind of understandings of their own sort of business operations as they do from the numbers that these things spit out. We talked about visualizations, and finally, I just want to leave you with a call to action, I guess. So, we've solved the big data problem as an industry. I think we're very good at that now. And I think it's time to get back to what we said at the beginning was the big picture. And that is developing software and tools that integrate data and systems and give users the kinds of insights that they need to solve the problems that they're dealing with at the level that they're dealing with them, rather than just where we stop today, I think, which is taking the data and providing ways to make the data itself as digestible as possible. I think we need to take the next step and try and help people understand the systems that they're dealing with as well as we can and put some of this amazing IT power we have to use in that effort. And with that, say thank you. This is one of the nice visualizations I was talking about. This is a way of visualizing arms flows between different countries. This is, I wish I was responsible for this, actually I'm not, but it's very inspiring, to me at least. And it shows a way of looking at how if you make certain changes and look at things, then the flow of arms between different countries in the world changes. It's this beautiful 3D rendered thing on the web. So look at all the arms flowing in the United States. It's kind of funny. Anyway, thank you very much, everybody. And, yes.
I just have a couple of observations.
Sure.
One of which is, to question whether or not big data has actually been solved, because there was an article last month or in March from the FT which says big data put on a big mistake. And 2 years ago there was another article in the New York Times which was, big data is great, but so is intuition, and big data is not providing the insights, not just the issue of whether or not the data is being presented, well visually. Because one of the, four bases of big data is that there's volume, there's velocity, there's variety, and there's veracity. However, I kind of want to, get the audience's opinion on whether or not, the audience thinks that there's actually veracity within the data. So that's my first observation. My second one is that the types of Monte Carlo simulation and the various neural networks models, I'm familiar with them because I used them 12 years ago within hedge funds to do portfolio asset allocation modeling and within risk management. So I can understand creating those likelihood scenarios of the profit bands, as it were, and then doing gradient descent accordingly, according to whether or not you can adjust those levers. But my sort of interpretation is that even the volume of big data at the moment, all of the data visual tools are still not going to sort of enable us, even as a basis framework, to actually get to decision intelligence. Decision intelligence in terms of akin to our own intuitions of how we should be making decisions, not just based upon what that gentleman over there said, which is environmental conditions external to our control. So competitors, market, even at the moment, the social feeds from the various networks, the social networks are affecting, the way in which we're kind of assimilating that information and then making decisions based on those communications that we're receiving.
Okay. Well, I guess it's a question for the audience, but if I could just respond to the first question first, and then I suppose I'll express an opinion on the second. I don't disagree with you at all. When I'm talking, I suppose the way I was referring to the big data problem being solved, as I said at the very beginning, there was just simply a mechanical problem of data collection, data storage, data access, and I think a huge amount of intellectual and material resources have gone into ways of collecting data very quickly, storing it, accessing it. And I think we've got to the point now that there's still cases where you could say, well, I wish I could get data about this, but it's just not feasible. If that's true, it's probably because what you're saying is very hard to measure, not because the data is very hard to manage. If you want data about who's talking to who, there's APIs into Facebook and all of those things that will tell you that very, very quickly. And I think we've come a huge long way in doing that. I agree, it's not finished yet, it's not done, there's always improvements. But is the major impediment to using data in quantitative analysis or quantitative support the fact that it's just very hard to manage data, period? I don't think that's true anymore. I think it is possible to, in most cases, to deal with data quite effectively. And there's 1,000 companies within 10 miles of here that will help you do that. And I was drawing that by contrast to understanding systems. There's maybe 20 companies within 10 miles of here that devote themselves to that particular problem. I guess what I'm saying is I think there's more value that can be extracted out of that we haven't extracted yet with our technological capabilities today, which we do. The second one, really quick. Yes, data is not the answer to everything. Of course it's not. And that's, again, one of the reasons why modelling is a fresh approach to that. Modelling doesn't just rely on data. It also relies on any information you care to prime the model with. And one of the things that we find, again, I talked very quickly about that sketch graph function. One of the reasons we introduced that concept was the ability to capture human intuition in a way that a computer can digest. So asking someone, well, how do you think this will behave? After a bit of elicitation, you can say, well, it's kind of like this, and they'll draw a sort of wavy line on the board. And no way do you want to try and turn that into an equation, but at this point, it's our best effort at trying to capture that. And I agree with you, and part of what we're trying to do is to say, look, you've got huge amounts of knowledge in the heads of your people that are not going into your quantitative analysis at all. And one of our little missions in the modelling space is to try and find ways not just of capturing hard quantitative data, but also that sort of softer human knowledge, and find ways of including that in the model. And I agree with you, that's hugely important. And I think that's another interesting area of research. How do you take soft knowledge and combine that with harder quantitative knowledge so that can also inform decisions? So maybe other people want to comment on that. Yeah.
Well, I have a question.
Sure.
In your experience with the development of this product and getting it in front of customers, what have you found to be the industries or the system types that have been the low-hanging fruit, where utilization of this tool has had immediate and tangible benefit? And what industries or systems have you found that this isn't immediately beneficial? And for those, what do you see as the challenges?
Yeah, okay. There's some global challenges, there's some cultural challenges, and that no one's actually thinking in terms of kind of this sort of approach to solving problems. So part of it, one of the reasons I like speaking at venues like this is just to introduce the idea and let people like you mull over it for a while and accept it or reject it as you wish, but at least be aware of it. And part of it is just kind of awareness. Where it's been particularly effective are places where there are the level of complexity of the decision making is too great for some sort of informal technique. It's got to be formalized. It's got to be assisted with some IT power. Some examples are, for example, resource allocation. So the US government, various branches of the government use our tool to do budget allocation across their various spending priorities. And the thing that they face is that they're always they're in a very dynamic environment. Congress is cutting back their appropriated funds, basically every year, yet they still have the same mission to deliver. So what they're trying to do is figure out, how do I optimize the cuts that I make to my spending in a way that least affects my outputs? That's actually a pretty tough problem they need to deal with, and this is one example of that. Another example is, it turns out that this is just a useful way of building financial models. So a lot of finance sector uses it for things like probability of default and credit risk rating and those sorts of things. For not for retail situations, because there's big companies that do that, but in sort of niche situations, like if they want to rapidly produce sort of ad hoc products for particular loan situations, or if they have very large deals where they're really going to do a dedicated risk model. There's a few major banks using it for this. Technology transformation is another. I mean, there's quite a few cases of that. Yeah.
So we just going back to the model that you created of your example. There was like 3,000 data points. For each vertical, what is the maximum or minimum? What does each of those represent?
Let me. Sorry, I'll get to that. Oops, too far. Right, there we go. So that's the profit that each trial yields.
Right. So what is the horizontal axis?
The horizontal axis is essentially each trial is a particular combination of the parameters. But each trial also gets a label: trial 1, trial 2, trial 3, trial 4. So what this is just the number of the trials. So this is telling us we did about 3,000 trials to produce this. And each one of the points along here is a particular combination. And in the tool, when you run it interactively, you can reproject that out and have the axis here saying, okay, I'm just going to look at one of the input parameters. Or you can roll your mouse over the curve and show you the combination of input parameters that went to that point. But it's just a way of showing, here's the aggregate output of my utility, or the thing that contributes to my utility function, which in this case is my profit, and that rolls up all of the different input variables so I can see the sort of whole thing at once.
I see.
Yeah.
And are you propagating error as well? So because you said there's
Yes.
error in input.
Yes. So that's a good question. So one of the harder things to do is to say, okay, given a given set of error bounds on my input functions, my input variables, what's the error on my output? And I didn't really do that this time, so I just assumed that those codes were perfect. But if you have ranges, then those will get propagated through as well. That's an interesting problem. You can't, naively you'd think, well, I'll just calculate for the lower curve and calculate for the upper curve. But that's assuming all of your functions are monotonic. And if they're not, or if they display sort of oscillatory behavior or something that's a bit more complex, then the biggest error may not come from the biggest error bounds on the input. It may be some intermediate value. So just doing that, you almost have to do that as a simulation within the simulation to do that. That's actually quite a complex sub-piece of this. It's just propagation of error under different circumstances.
Let's stop questions here and let folks leave if they need to. Thank the speaker again.
Okay, thank you very much.
Oh, that's okay.